30th lecture, and we are going to discuss a new two-port description, that means the scattering matrix description of a two-port. This description, scattering matrix description, is not confined to two ports only. It can also be applied to multi-ports. However, our discussion shall be in the context of two ports only. The scattering matrix description is particularly important in networks in which the space variable is to be taken into consideration. What are such networks called? Distributed networks, as opposed to lumped networks. Therefore, scattering parameters are important descriptions in networks which have to consider, in addition to the time variable, the space variable also. In other words, in distributed networks. Nevertheless, they are equally applicable. They are quite general parameters. They are equally applicable to lumped networks also, and it is appropriate that at this stage we know about scattering matrix parameters, particularly when you have a course on electromagnetic theory and its applications, and you learn about microwaves. Scattering matrix shall be the only description, either a field description or a scattering matrix description, and this scattering matrix description is in terms of incident power, is in terms of power instead of voltage and or current. It is in terms of incident power and reflected power at a particular port. If you take a network N, and at a particular port, as you know, at very high frequencies, it is impossible to define a voltage. You have to go for field descriptions, that is electric field and magnetic field. However, power, which is E cross H, is as fundamental a quantity as the electric field or magnetic field. It is a combination of electric and magnetic fields, and at those frequencies the only description that is suitable and works is the power description, and that power description brings in the parameters called scattering parameters. Now, it is convenient to think in terms of incident and reflected power at high frequencies. You could also do that at low frequencies, nobody stops you, but at low frequencies it is usually more convenient to describe a network in terms of voltages and currents. Voltage and current as the variables, and therefore Z parameters, Y parameters, H and transmission parameters, they describe the network quite well. But since scattering matrix parameters are universal, that is, they can be applied to low frequency as well as high frequency networks, we shall deal with them in a very general manner. Most of our examples will be with regard to lumped networks, but we would also like to look at one specific form of a distributed network, namely a transmission line. In fact, we shall do that in order to facilitate the definition of scattering matrix parameters, and you will understand the physical significance. I could do this mathematically, that is, define the incident variable as this and the reflected variable as this, and so on and so forth, but let us go a bit into the physical interpretation, that is the link of scattering parameters with power. And this necessitates that we know a little bit about transmission line theory. I do not think you have been taught transmission line theory yet, or you are having it now. Okay, we shall therefore. Oh, very good. Then my job is simplified. The transmission line, the telephone line for example, or the power line that goes overhead, typically it consists of two lines like this. They usually run parallel to each other, two lines like this, and any other transmission line can be described by a parallel wire transmission line. For example, a coaxial line is also a parallel wire. There is an inner core and there is an outer shield. Outer shield is at a constant distance from the inner core all through the length of the cable, and therefore almost all transmission lines can be described in terms of a two-wire line. And and you know that the space variable here is an important parameter. If we consider this as x equal to 0 and x equal to L, then an excitation here, for example an input step voltage, does not appear at the output instantaneously, it appears after some delay, and this is why the space variable becomes important. You also know that a transmission line like this is described by 4 parameters R, L, G and C, okay, where R and L are the series resistance and series inductance per unit length, and the G and C are respectively the conductance and the capacitance per unit length. These are shunt parameters, whereas these are series parameters. And you also know, since you have done it, that a transmission line is described in terms of 2 instead of the 4 primary parameters, as they are called, the primary constants. You can have a description in terms of just 2 derived parameters, namely the propagation constant gamma, which is equal to, for sinusoidal excitation, it is the product of R plus j omega L, G plus j omega C, the product of this, and the characteristic impedance Z0. This is the propagation constant and this is the characteristic impedance Z0, which is equal to square root of R plus j omega L divided by G plus j omega C. It is the ratio of the two, the impedance, series impedance per unit length and the shunt admittance per unit length. It is the ratio of the two, square root of that. Do the dimensions agree? G is 1 by resistance, so it is impedance squared, square root of impedance squared is impedance. Okay. What about the dimension of gamma? Dimensionless. And you also know that gamma is a complex quantity. In general, it has a real part alpha and an imaginary part beta, J beta, where the real part alpha is a positive quantity, okay, positive quantity. The voltage and current at any point of the line, let us say x, distant x from the origin, from port number 1, this is port number 2, the voltage and current at any point, if we denote this by V of x and the current is denoted by I of x, well, this voltage and current in general are not only functions of time but also functions of space variable. We have considered only one dimensional propagation. If it was a space propagation, for example, propagation of a disturbance created by an antenna in an otherwise still environment, well, it travels in all the 3 directions and therefore 3 variables would have been needed. Here it is a guided wave, guided along the transmission line, so the propagation is only along one direction, which you conveniently call the x direction. Okay. If the excitation is considered sinusoidal, then the quantities capital I and capital V are phasors. You can take either the peak value or the root mean squared value, depends on your convenience. These are the phasors, and then time dependence is taken care of by making it into a phasor, and only the space dependence x has to be taken care of. And you know that this is only a review, I am not going into the details. You know that the basic equations for transmission line behavior is dV dx equal to minus Z I, where Z is R plus j omega L, that is the series impedance per unit length, and the other equation, the current equation is d I dx equal to minus capital Y times V, where capital Y is equal to G plus j omega c, and a combination. These are two coupled equations, voltage current, current voltage, they are coupled equations, and if you eliminate one of them, for example, if you differentiate this and substitute for I, then you get a second order differential equation in the voltage. d2v dx2 would be equal to gamma squared v, where gamma squared is simply the product zy, and gamma obviously is the propagation constant, and therefore the solution is very easy because it is a second order differential equation without the first order differential coefficient, and the coefficient of v is a constant gamma squared, and the solution is v of x equal to some constant vi e to the minus gamma x plus some other constant Vr e to the plus gamma x. All right. It will have two independent solutions, and gamma can have the value of plus minus. Gamma has the value square root zy, and the auxiliary equation for this shall have the roots m equal to plus minus gamma, and that is why this solution comes. You have done this solution earlier. Okay. And you know that this term, the subscript I stands for the incident wave and the subscript R stands for the reflected wave. Can anyone recall why this is called an incident wave? Direction of gamma. You see, the voltage as it traverses the line must decrease with distance because it is a passive network. It is a passive network. And the real part of gamma is the attenuation constant. Therefore, as x increases, the attenuation shall increase, and therefore this is the incident wave, a wave travelling in the direction of positive x, and this is the reflected wave, that is a wave travelling in the negative x direction. This is the incident wave and that is the reflected wave, and if you substitute this in the equation I equal to minus 1 over z dv dx, if you substitute this solution, then you get the solution for I, and it can be written as Vi divided by z0 e to the minus gamma x minus Vr by z0 e to the gamma x. That is the incident current. This is the incident current and this is the reflected current. There is a sign change, there is a negative sign here. Okay. Now these are our basic equations for a transmission line. V equal to Vi e to the minus gamma x plus Vr e to the gamma x. These are our basic transmission line equations, from which now we shall go into the scattering matrix description. If there is a question at this point, I would be happy to answer.
So shouldn't this be multiplied by gamma, the equation of I? Because we are differentiating V.
Oh, okay. If
So
you are
it's divided
differentiating,
by Z naught.
that's right. If you are differentiating by V, gamma comes, yeah. But then this is also divided by Z.
It is 1 by Z
Gamma by Z
is Z naught.
is Z naught. That is correct. No, gamma by Z is not Z naught.
1 by Z.
1 by Z naught. Okay, that's how this 1 by Z naught comes. Okay, I certify that these two equations are correct. All right. Yes.
So in the initial diagram here you show the transmission line.
Yes.
So you are considering the reflection at which point?
Reflection at which point? At any point in the transmission line, the voltage component can be thought of as the superposition of two voltages, one travelling in the forward direction and the other travelling in the backward direction. And the one travelling in the reverse direction is called the reflected wave. Now reflection can occur throughout the line. Reflection occurs at every point in the line. and it is the sum total of that you see. VR e to the minus gamma e to the plus gamma x is the reflected wave, which is a sum total of reflections at all points for which the coordinate is greater than x. Okay? Yeah.
So is the forward direction considered as positive? X is positive.
Forward direction is considered as positive because our coordinates were x equal to 0 and x equal to L. Now this is quite arbitrary. It depends on where you connect your source. Obviously, we have connected our source as port number 1. So as we go away from this source, x is positive. This is considered as the origin.
So that means reversing the source will.
That means if I connect the source here, then I will consider x equal to 0 as this point, and the wave travelling in this direction from right to left will be considered as the incident wave.
So that will be positive.
That's right. That is right. Our direction will change. X equal to 0 and x equal to L. So x increases in this direction. Okay, it's a matter of convention that we always take the source at the left. Nothing to do with political inclinations. Source at the left and the load at the right. Okay, this is our convention. You see, in drawing networks, the left two terminals, we call it port number 1. There is nothing sacred about exciting at port number. You could excite at any other port. In fact, when you go to microwaves, you will see the magic T, for example, is a 3-port network. There are networks which are 6 ports, and there is nothing called input port output. You could excite at 3 ports and take the output at any of the other 3 ports. Okay? There are ring couplers in which it could be n number of ports, n can be greater than 6 also. There is nothing sacred. As far as 2-port is concerned, we stick to the convention that we excite at the left and take the output at the right, which also we have broken. You see, in stating the reciprocity theorem, for example, we interchange the source and the load. Okay? So there is nothing sacred. Any other question? We start from these two expressions. Let me write these expressions again. V equals to Vi e to the minus gamma x plus Vr e to the gamma x, and I equal to Vi divided by Z naught minus e to the minus gamma x minus Vr by Z naught e to the gamma x. Now I can write this second equation. I do some mathematical manipulations now. I can write this second equation as IZ0 equals to Vi e to the minus gamma x minus Vr e to the gamma x. All right. If I combine this equation with this equation 1 and 3, then I can find out expressions for Vi e to the minus gamma x in terms of capital V and Iz0. What I simply do is V plus Iz0 divided by 2. All right. On the other hand, the reflected wave Vr e to the gamma x can be written as V minus Iz0 divided by 2. Is that okay? That's very simple, simple manipulation. The next thing that I do is I take 1 by square root Z0, I beg your pardon, I take square root Z0 common. All right. Then what I get is half square root Z0 out of this expression I take out. Then I get and half. Okay. So I get V divided by square root Z0 plus I square root Z0. All right. And I write this as square root Z0 half V by square root Z0 minus I square root Z0. All right. There is a purpose in doing that. Before I go into why I did this manipulation, let me also point out to you that if the transmission line is terminated in its characteristic impedance, okay, then what happens? There is no reflected wave. Well, the reason is from here you see, if V is equal to Iz0 at x equal to L, what does termination mean? it means that at the end of the line you have a termination Z0, this is V of L and this current is I of L. So, VR e to the power gamma L shall be equal to V of L minus I of L Z0, which is equal to 0, alright, because this says that V of L is equal to I of L Z0. You see this point? Okay. Therefore, VR e to the gamma L would be equal to 0. Now, e to the gamma L cannot be equal to 0 unless L is infinity. No. Okay, L is minus infinity. Therefore, this constant VR must be equal to 0, which means that there is no reflected wave, and if there is no reflected wave, then these two terms shall be 0, these two terms shall be 0, and you see that the ratio of V to I at any point on the line shall be exactly equal to Z0. In other words, a characteristic impedance terminated line at any point inputs an impedance of Z0. Okay? The input impedance of a characteristic impedance terminated line is equal to Z0 wherever the impedance is measured, irrespective of where the impedance is measured. Alright. Now let us go back to this this manipulation. We have shown that Vi e to the minus gamma x, let me write this again, equal to Z0 half V by square root Z0 plus I square root Z0, and VR e to the gamma x equal to square root Z0 half V by square root Z0 minus I square root Z0. Now, these were done with reference to a transmission line. Okay? We found out expressions for the incident voltage wave and the reflected voltage wave. Now, let us consider a general 2-port. Forget about transmission line. A general 2-port N, general 1-port to start with. Okay? A 1-port has only 2 terminals where you can connect a voltage source, measure the current, or connect a current source, measure the voltage. Suppose the voltage current description we do not want, we want a different kind of description in terms of power, alright. Then what you do is you define for every such 1 port a constant R0, which is called a reference impedance. Actually it is a resistance. Okay, resistance is a special case of an impedance. So it is a reference resistance. Alright. Well, let us put the term impedance, reference impedance. All we want is that this should be, and for the present let R0 be arbitrary. We choose, we define, we call R0 as an arbitrary reference impedance. We will show later how to choose R0, but given a 1 port N, we define an arbitrary reference impedance R0, and then we make the following definitions. We say
R0 is reference for the whole of the network or just for this particular port in case it's a 2-port doesn't matter?
no, we are now confining to 1 port only. Then while extending to 2 ports, we will have to define 2 such reference resistance.
It's just
No, it's for the present it's arbitrary. We will see how to fix it later. For the present it is arbitrary. And then we define an incident parameter A and a reflected parameter B as follows. We define an incident parameter A and a reflected parameter B, not parameter, a variable. Okay? Instead of voltage and current. Now we will see how A and B are related to incident power and reflected power later, but at the present time we simply say it is a variable. We do not know how it is related to power, but we define like this. We define A, incident parameter, as half V by square root R0 where let V and I be the voltage and current at this port, Okay. Then what I do is A we define simply this term, that is if Z0 is square root Z0 is taken out, then whatever this term is, this is what we define as A, which means that we define this as I square root R0. You see, this is the incident, you can see the relationship between the incident voltage in a transmission line and the incident variable of the one port. Okay. And B is called the reflected variable, and it is defined as V by square root R0 minus I square root R0. Okay. These are the two quantities, two variables which are defined for the one port N in terms of conventional voltages and currents. Ultimately we can do away with voltage and current. All right. Now, for being applicable to lumped networks in which you can work in terms of voltage and current, there must be a relationship, and this is the relationship that we have that we take care of in the definition. And if you see these two expressions and the definitions of A and B, you see that A and B are very simply related to the incident voltage wave in a transmission line and the reflected voltage wave in a transmission line. You can see that if R0 equal to Z0, if the reference impedance is the same as the characteristic impedance, then in a transmission line A is simply equal to the incident voltage wave divided by square root of Z0. Agree? Therefore, A is indeed connected to an incident variable. Okay. Similarly, B, as you can see, is VR, the reflected voltage wave divided by square root Z0. So, A and B have a physical interpretation. We are not considering the dimensions at the moment. The dimensions obviously are not voltage, because they are voltage divided by square root of an impedance. So, it would be volt per ohm to the power half, all right, or volt ohm to the minus half. Agree? We are not bothering about it now. We shall relate ultimately A and B to power, and then you shall see the peculiarity of this definition shall become obvious, because our main concern is to describe the network in terms of power as the variable. All right. But as far as a one port is concerned, these are the definitions of the incident and the reflected variables. We are not saying voltage, current or power.
That means choosing R not different from Z not, we cannot define A and B.
Pardon, I beg your pardon?
So choosing R not different from Z not, we cannot define A and B in terms of VI and VT.
No, that is not correct. I can choose R naught anything I like, all right. Then my VI e to the, for a transmission line, it will not be as simple as this. It would be a different kind of a relationship. But why should one do that? Because after all, our purpose is to describe the multiport, describe the two port in terms of variables and parameters. Okay. So, it is convenient. Similarly, here also in the case of one port, you will see how to choose R naught to make life simple. Instead of going into complicated calculations, we can bring out things very easily by particular choice of the characteristic impedance, and we will see how to do that. For a transmission line, you are quite right, it is chosen as equal to the characteristic impedance in fact at both ports.
Then we are not concerned with other values of R.
In transmission lines, we don't concern ourselves. Yes, that is true, because it simplifies things, it simplifies matters, and it also fits in physically the interpretation of incident power, reflected power, the Poynting vector, and so on and so forth. But let us go back to a one port. In order to understand the physical meaning of A and B a little better, let us consider power. As you know, the power absorbed by a network N, when it is excited by a sinusoid capital V and the current is I, the power, as you know, is given by real part of V I star. Do you know this? Complex conjugate, alright. Can you derive this? Well, for historical reasons I will use the factor half, which means that I am considering V as the peak vector, not the RMS vector. Okay? The phasor is considered with the peak value. For example, if I have Vm sin omega t, then my voltage vector is Vm, the peak value, the maximum value, not the RMS value. And this is historical. You can do away with half, then it is implied that capital V and capital I are RMS vectors. Okay. Now, the derivation of this, can you give me a very simple way of deriving this? All I am interested in is whether you know how to derive this. Okay. If you know, we'll skip it. All right. Now, V and I, you know that A is equal to, by definition, A is equal to half V by R square root R naught plus I square root R naught. My intention now is to express P in terms of A and B to get an interpretation of A and B in terms of incident and reflected power. So, this is half this minus this. Okay. Now, if I eliminate, now if I find V and I in terms of A and B, do you have a question?
So the A and B are expressed in the peak value of B.
That's right. That is correct. That's why I took the factor half here. So you can easily see that A plus B times square root of R naught, okay, is simply equal to V. Isn't that right? And similarly, A minus B, this factor of half, because twice into half becomes equal to 1, A minus B square root R naught becomes equal to I. So, the power absorbed by the network, A minus B divided by R naught, yes, thank you. Okay. So, the power absorbed by the network is half real part of V, that is A plus B multiplied by R naught, and R naught shall cancel, square root R naught, and therefore multiplied by A star minus B star, and the real part of this is simply A star minus B star. The rest of it will be the imaginary part. Okay, A star minus B star, which I can write as half mod A squared minus half mod B squared. And you can see that the power absorbed by the network has been expressed in terms of two quantities, a positive quantity and a negative quantity. Therefore, this can be interpreted as the incident power, that is the power that is tried to be fed to the network by the source, and this power half mod B squared is the reflected power or the power that is rejected by the network and sent back to the source. Okay. The total power absorbed by the network is the power that is fed in and the power that goes out. The rest of the power remains inside the network and is dissipated. If this was a lossless network, then mod B squared would have been equal to mod S squared, because no power would have been absorbed. But in a passive network, this shall be greater than or equal to 0 because of passivity. Okay. If it is 0, then it is passive and lossless. If it is greater than 0, then it is passive and lossy or dissipative. Okay. Passive and dissipative. And therefore, from this we get an interpretation of the incident variable A and the reflected variable B in terms of power, that is A star divided by 2 is the incident power, B star divided by 2 is the reflected power. Alright. And this is how the two variables are related to physical quantity like power. First we related to voltage and current, but that, as I said, holds only if you can measure the voltage and current. In a microwave network, no, sorry, you cannot put a voltmeter across a waveguide, for example, and measure the voltage. No, it's not possible. It's a single metal, and therefore you have to measure the power. Okay, now let's go back to A and B. A is the incident variable. Yeah. Yes, was there a question? A is the incident variable and B is the reflected variable, and one defines a relationship between B and A of a one port like this. The reflected variable is put as some constant capital S multiplied by the incident variable A, and capital S is called the scattering parameter of the one port N. In a one port, if we had the impedance description, Z parameter description, all that you can define is the input impedance. In a one port, if you want to have a admittance description, all that you have is the input admittance. Similarly, in a one port, there are only two variables, and therefore you can express one in terms of the other, and capital S is a scattering parameter and is a constant for the one port, capital S. Capital S is also called, for a one port, it is also called the reflection coefficient. And to see why it is called a reflection coefficient, you see that if you look at the definitions of B and A, capital S is the ratio of B to A, and if we cancel out the factors half, then we get this as V minus I R naught divided by V plus I R naught. If we apply the definition and cancel out the factors half, multiply by square root R naught, then this is what I get. And you can see that if I divide both numerator and denominator by capital I, then I can write this as Z minus R naught divided by Z plus R naught, where Z is the input impedance, that is, it is the ratio of V by I. Okay? And as you know from transmission line theory, this is called the reflection coefficient or the mismatch coefficient. That is, how much Z, the input impedance, is away from the reference impedance. Okay? So this is also called the reflection coefficient. You can see that if the reference impedance R naught is chosen equal to Z, then the scattering parameter is 0. Okay? This has something to do with the choice of R naught at a slightly later stage, but let's look at a situation in which we have a real source, and a real source is a voltage source with an internal impedance in series, or a current source with an internal admittance in parallel. Let's take the voltage description of the real source, a VG and an R sub G.
Sir,
Yes.
so S is equal to B by A. So if B is equal to A, that means the input power is, if the squares are also related under roots, that means that the reflection, the reference impedance that we have fixed, that is 0.
Say it again.
So because S is equal to B by A,
Yeah.
if that is,
If the
that means
reflected,
it's lossless. If the one
Okay.
network is lossless, then that means that z minus rho by z plus rho is equal to 1.
Okay. If it is lossless, all that it means is b mod b squared equal to mod s squared. Does that mean that b is equal to a? No, not necessarily. Okay. Magnitude squared may be equal, but the complex quantities may be quite unequal. For example, x minus jy and x plus jy, they have the same mod, but the quantities are different. We will come to this when is the scattering parameter equal to 1. We will come to this a little later. Have a little patience. Let us have a network n. Let us have a network n which is driven by real source Vg and Rg, and let the voltage V and the current I be defined like this, and at this point let us define an incident parameter A and a reflected parameter B at the input of the network. Alright. We have defined voltage, current, incident parameter, reflected parameter. Now we also choose R0 as equal to Rg. Okay. We choose the reference impedance to be the same as the input impedance as the internal impedance of the source. Okay. Right. This was arbitrary, so we can choose it. Let us choose it to be equal to Rg. Then let us see what is capital V. Okay, this is a choice. Capital V is Vg minus I Rg. Okay, or capital I let us also suppose, let me use, I am running out of colors. Okay, let us also suppose the input impedance is equal to capital Z, input impedance of the one port. We have defined Vi, so the ratio of V by I is Z. Okay, then don't you see that capital I is simply equal to Vg by Rg plus Z, alright, Vg by Rg plus Z. This is perfectly alright. Now let us look at what happens to A and B. No? The current here is simply voltage divided by Rg plus the impedance. Okay. Let us see what happens to A and B. A is equal to 1 by 2 V by square root R0 plus I square root R0. Let us not impose R0 at the present state. We will see what happens when R0 equal to Rg a little later. Let us keep the identity of R0 for the present. I can write this as 1 by 2 square root R0. If I take square root R0 out, then I get V plus I times R0. Okay, and V is Vg minus IRg, Rg multiplied by Vg divided by Rg plus Z. I substitute for I, plus I times R0. So it would be Vg R0 divided by Rg plus Z. Is that okay? Is this equation okay? What I did was I skipped a couple of steps, but let me introduce them. This is 1 by 2 square root R0 V plus I R0. For V I write Vg minus I times Rg plus I times R0. Okay. All right. Right. So this I can now simplify to Vg I can take common from all the three, divided by twice square root R0 1 plus R0 minus Rg divided by Rg plus C. Now what will happen if R0 is equal to Rg? The second term obviously becomes 0, isn't that right? If the reference impedance is chosen as equal to the internal impedance of the source, reference impedance so far was arbitrary. If this is chosen to be equal to this, then my A simply becomes Vg divided by twice square root R0. Not R0, no longer R0, Rg. Okay? So far so good? Alright. Now let us look at the power P. As you know, the power is half mod A squared minus mod B squared, which is equal to half A squared. If I take this out, what shall I get in the bracket? 1 minus mod S squared, because S is B by A, alright, mod S squared. You also know that capital S is equal to reflection coefficient, that is Z minus Rho divided by Z plus Rho, and Rho Rg, okay. Rho has already been chosen to be Rg. Therefore, if Rg, if Z equal to Rg, if the input impedance, if the network is so designed that the input impedance is equal to the internal impedance of the source, then S is equal to 0 identically, and therefore the power simply becomes the incident power. There is no reflected power, and all the power that is fed to the network is absorbed by the network. So the power becomes equal to half mod A squared, and if you substitute the value of A, then you get Vg squared divided by 8 times Rg, Vg squared divided by 8 times Rg. Alright. Now, if you recall the theorem of maximum power transfer, you know that maximum power is transferred to a network if the internal impedance of the source is the complex conjugate of the network impedance. You know this, don't you? Okay. Here the internal impedance is resistive Rg. Therefore, if Z equal to Rg, then maximum power is transferred, and therefore this power we can call the maximum available power. That is, I am going very slow because these terms are new. Maximum available power is the power that is the maximum power that can be drawn from a source generating an open circuit voltage Vg and having an internal impedance Rg. You cannot draw a power more than this. Yes. If you have a source which generates a peak voltage of V sub g, peak phasor V sub g, and a internal resistance Rg, you cannot draw from this source a power greater than this, because by the maximum power transfer theorem, maximum power can be transferred from this source only to an impedance which is exactly equal to Rg, and if you terminate this in Rg, the power that is transferred to Rg is exactly equal to this. Therefore, this power is called, the name for this is maximum available power. Okay. And our final conclusion is that if you have a one port which is supplied from a voltage source Vg and internal impedance Rg, then maximum available power will be transferred to the load PA equal to Vg squared by 8 Rg when the reference impedance R0 is chosen to be equal to Rg. Not only that, the network is such that its input impedance is equal to Z. No more transmission line, it is a simple one port which is equal to V by I. Alright. Okay, so given a one port, one first identifies what is the internal impedance of the source and chooses that as the reference impedance, and then if the one port is to be as effective as possible, you should design the one port so that its input impedance is equal to the internal impedance of the source. And in that context, we go back to the definition as capital S is Z minus now Rg, which is the same as R naught divided by Z plus R naught, and you can write this as small z minus 1 divided by small z plus 1. Okay, I divide by where small z equal to cap Z divided by R naught. Obviously, small z is a normalized input impedance of the network, and if we decide to what is capital S normalized? No. The scattering parameter is as usual, it does not change, it is not normalized. What is normalized is the input impedance of the network, normalized with respect to the reference impedance. Now, follow me carefully. If we decide to work with small z, the normalized input impedance, then obviously our reference impedance is now 1 ohm. And this is the convention. You will see if you study microwaves later that one always talks of 1 ohm normalized impedance, 1 ohm reference impedance for the scattering parameter, which simply means that all impedances are divided by the actual source impedance, alright.
Source impedance or characteristics?
Source impedance has to be the characteristic impedance
Or maximum power?
if it has to give maximum power to the transmission line. Okay. Now, so we would like to make a few comments about this relationship Z minus 1 divided by Z plus 1 and then close the class. Okay. A few comments about this. There was a question about B equal to A. B equal to A, then capital S equals to 1, alright. That means no power is absorbed. There is another way that capital S can be equal to 1. Suppose the network, the one port is an open circuit. That means small z equal to infinity. Don't you see that capital S is equal to 1? Okay, capital S is equal to 1. Similarly, if the network itself is a short circuit, then capital S is equal to minus 1. These are two special values for open circuit and short circuit. Capital S equal to 1 for open circuit, capital S equal to minus 1 for a short circuit. Alright. Another characteristic or property of capital S comes into transparency if we look at this expression, half S squared 1 minus mod S squared. This was the expression for the power absorbed by the network, and you know that this is greater than or equal to 0 for a passive network. What can you say about mod S squared then? So mod S squared must be less than or equal to 1. It can also be equal to 1. Okay. So for a passive network, the scattering parameter, now it's a parameter, scattering parameter or the reflection coefficient magnitude squared must be bounded to unity, bounded by unity. It cannot exceed unity. For a reactive network, And what is a reactive network? A reactive network is composed of only reactances. Reactive network. Reactances means inductances and capacitances which do not dissipate energy. In other words, a reactive network is also a lossless network. For a reactive network, magnitude S squared shall be equal to 1. Alright. The third property of capital S shall be proved next time after defining a couple of important complex variable functions. We require a bit of mathematics, but it's not much. There is nothing to be afraid of. This is what we will do on Thursday.